So, good morning to all of you. In previous session, we had discussed the impulse response of a linear time invariant recursive system. We identified the impulse response of recursive LTI system by solving the given difference equation. And in case of recursive LTI system, the impulse response is simply the zero state response of the system, right? So today we'll be discussing correlation of discrete time signals. So basically we'll be discussing two types of correlation, that is cross correlation and autocorrelation. Okay. So we'll be discussing correlation of discrete time signals. So in case of correlation, basically it is a mathematical operation and it closely resembles convolution operation, right? So in case of correlation, there are two signals which will be correlated, right? The basic objective of this correlation operation is to identify or to measure the degree to which the two signals are similar, and we specifically extract the information which depends on the application of this correlation operation, in which domain that correlation operation is applied, basically, right? So basically two signals are involved in this correlation operation, and we'll measure the degree of similarity between these two signals depending on whether these two signals are distinct. If those two signals are distinct, then that operation is called as cross correlation, and if we are comparing signal with itself, okay, then it will be called as autocorrelation. So there are two types of this correlation operation, that is cross correlation and autocorrelation. In case of cross correlation, two distinct signals are compared with each other. Just for example, if I have taken the photograph of one of the student and I am comparing that photograph with other students photograph, then there are two different signals which are compared with each other, then that operation can be called as cross correlation. In case of autocorrelation, just for example, student entering in the class at 8:30 a.m. So I have taken a photograph of that student and I am comparing the photograph of the same student taken at some different time, just for example at 6:30 p.m. But those two photographs belong to the same student, so I am comparing two same signals here. Okay, so I will be applying correlation operation and I will be measuring the degree of similarity between these two photographs of the same student. So I have to use autocorrelation operation. So basically correlation can be used in various applications. So the correlation of signals can be performed in applications such as radar, sonar, even it can be used in digital communication, geology, seismology, right, image processing, and so on. Right? So just for example, if we are considering two signals such as x of n and y of n are two signals, right? So these, if we want to compare these two signals, and here we are considering, just for example, in case of radar or maybe active sonar application, if we consider this x of n as the transmitted signal, right? So obviously when you are using radar application, so from radar one frequency will be transmitted that strikes to object which is in a particular range, and after striking that once that signal gets strike to that object, it will get reflected back, and it will get received back after certain delay. Okay, so that signal can be represented as this y of n, which is nothing but the received signal. Okay, in case of the radar application. So obviously these two signals used to identify or locate the position of object which are flying in the air or which is located at some location, right? In case of radar application, so its coordinates will be located according to the after what time that signal has been received back. Okay, the transmitted signal has been received back. Okay, at the radar. So basically these two signals are there, that is the transmitted signal and the received signal. Okay, so if a target is present in the space being searched by the radar or sonar, the received signal often consists of a delayed version of the transmitted signal, right? So that means your transmitted signal will get received back, but so simply if a target is present in the space being searched by the radar or sonar, the received signal often consists of the delayed version of the transmitted signal, that is x of n. So x of n will not be received as it is, obviously it will get delayed by certain amount of time. So when it will be received, so once it strike to that object in the space, okay, so once that signal strike to the object, then it will get reflected back and it will be received after certain delay. So obviously this received signal y of n will comprise the delayed version of the transmitted signal x of n, which is reflected from the target, and it may get also corrupted with some additive noise. Okay, so basically we can represent this received signal y of n in terms of the transmitted signal x of n as it comprises the delayed version of the x of n. So x of n may get delayed by the time capital D, right? And it will also have some additive noise into it. So W of n will represent some noise, okay, which has been added into the transmitted signal, and this signal get attenuated by the attenuation factor, just for example alpha, right? So what we have transmitted in this space, so we have transmitted signal x of n in this space, but in the response to this x of n transmitted signal, once this signal has been strike to the target available in the space, okay, so it will get received back in terms of this signal, that is y of n, which comprises the delayed version of the transmitted signal. It has been added with certain additive noise, right? And there will be certain attenuation. So this alpha represents the attenuation factor, the with which the signal loss involved in the route trip transmission of the transmitted signal x of n. Okay, so alpha is the attenuation factor representing the signal loss involved in the round trip transmission of the signal x of n, while capital D is simply the delay, or it can also be called as round trip delay, assumed to be an integer which is multiple of the sampling interval, while W of n is the additive noise picked up by the some devices which are available there, such as antenna, and it can be any noise generated by the electronic components and maybe amplifier contained in the front end of the receiver. Okay, so obviously we need to compare the transmitted signal and this received signal. Okay, so for comparison purpose we can use correlation operation here. So if there is no target in the space searched by the radar or sonar, the received signal will often consist of noise alone. Okay, that means you will not get this transmitted signal back. Okay, if there is no object available in this space, okay, or no target available in this space. Okay, so simply in return you will get noise only. Okay, so there will not be any transmitted signal available in the received signal, right? So having these two signal sequences, that is x of n, which is called the reference signal or the transmitted signal, and y of n as the received signal, the problem in the radar and sonar detection is to compare x of n and y of n. to determine if a target is present, and if so, to determine the time delay capital D, and to compute the distance at which that target is present. Okay, so the signal x of n minus d, that is the received signal which has been delayed by uh, which is nothing but the transmitted version of the signal, which is delayed by capital D amount, is heavily corrupted obviously due to the additive noise. So to the point where visual inspection of y of n is not reveal the presence of object in the space, or where you are searching it, right? So obviously for this purpose we can use this correlation operation. So correlation provides us with a means for extracting this important information of from signal y of n. So what information we can retrieve by using the correlation operation? We can retrieve at what position that target is present. Okay, by what delay that signal has been delayed, right? So according to that, by getting that information, we can compute the position of the signal there, right? So, as I have already stated that there are two types of correlation, that is cross correlation, right? And the second one is the autocorrelation, right? So, while performing the cross correlation operation, there are two signal sequences, that is x of n and y of n. So these are two distinct sequences, maybe representing two different signals, distinct signals. Okay, so the cross correlation of these two signals is represented as rxy of small l. Okay, so which is equals to, simply it is given by the formula summation n is equals to minus infinity to infinity x of n into y of n minus l, right? Small l. So, or it is equivalently given as simply r xy of l is equals to summation n is equals to minus infinity to infinity x of n plus l into y of n, right? Where this small l is called as uh, time shift or lag parameter. Okay, so it is called as shift or lag parameter, right? And basically this subscript, that is xy, represents which signals you are correlating. So we are correlating x of n with y of n here, right? So therefore in suffix or in subscript we are indicated xy there, right? So basically the order of these subscript, or these x and y, represents which signal has been correlated with another signal, right? Or the direction of the correlation. So that means you can also represent the correlation as ryx of l. So in this case y of n is correlated with x of n, while in this case x of n is correlated with y of n. Okay, so the formula for ryx of l can be given as summation n is equals to minus infinity to infinity y of l into x of n minus l, right? So here you are correlating y of n with x of n. Okay, sorry, here y of n should be there. Okay, so here it was x of n was correlated with y of n, here you are correlating y of n with x of n, right? So, and if I want to compare this rxy of l with ryx, so it will be rxy of l will be equals to ryx of minus l, right? So this is the relationship between rxy and ryx, okay, when you are correlating these sequences, right? So this is what how this is how you are representing the correlation of two sequences, that is x of n and y of n. Okay, so how will be basically we will be using this formula, that is correlation, cross correlation, Basically we'll call it as what, cross correlation of x of n and y of n, as we will be using this formula r x y of L is equals to summation n is equals to minus infinity to infinity x of n into y of n minus L. Okay, and if you compare this cross correlation or correlation formula with the formula of convolution, okay, what formula we have seen for convolution? So it was y of n is equals to summation k is equals to minus infinity to infinity x of k into h of n minus k. Okay, so convolution operation, it involved four different operations. First was the folding operation, right? So in case of convolution operation, what we have convolved, so we have convolved the impulse response. Okay, so from h of k you have obtained h of minus k. So initially we have performed the folding operation, next we have performed the shifting operation, right? So the folded sequence has been shifted by n samples, right? Next we have performed the multiplication operation. So the this impulse response has been multiplied with the input sequence. Okay, and finally we have performed the summation or addition operation. Okay, so whatever the product sequences that obtained here, that is the product of input and impulse response obtained here, all those product sequences has been added. Okay, so that was the last operation performed in the convolution operation. So convolution involves these four operations, while if you compare this with the correlation, so in case of correlation, x of n and y of n has been kept as it is. Okay, that means we are not performing the folding operation. Okay, but we are performing shifting operation, so the y of n has been shifted by L samples, right? Then we are performing the multiplication operation, and then finally we are performing the summation or addition operation. So in case of correlation, three operations are involved. First one is the sorry this folding operation we are not performing in case of correlation operation. First one is the shifting. Okay, so in case of convolution, we are performing folding operation. H of k has been folded or represented as h of minus k. But in case of correlation operation, y of n has been kept as it is. Simply we are shifting that y of n by L sample. Okay, depending on the value of L. Second, we are performing multiplication. Okay, and third we are performing addition or summation operation. So the correlation of two sequences involve three operations. These three operations. Okay, so therefore this correlation operation is closely resembles this convolution operation. Only the difference between convolution and correlation is that in case of correlation we are not performing the folding operation, right? So that is for what, cross correlation. And the difference between cross correlation and autocorrelation is that in case of autocorrelation you are comparing same sequence with itself. Okay, so I already given that example. If you are comparing your own photograph with your photograph only, right, only those photographs might be taken at different time intervals, right? So that can be considered as autocorrelation operation, and if you are comparing your photograph with another person's photograph, then it can be considered as cross correlation operation. So the autocorrelation formula, the formula for cross correlation were represented as Rxy of L is equals to summation n is equals to minus infinity to infinity x of n into y of n minus L. Okay. So in case of autocorrelation, x of n will be compared with itself, right? So the formula for that will be Rx x of L. Okay, is equals to summation n is equals to minus infinity to infinity x of n multiplied by x of n minus n. Okay, so this is the formula for what? autocorrelation, right? So in case of cross correlation, there are two different signals, that is x of n and y of n, right? But in case of autocorrelation, you are comparing same signal with itself, okay? Only that might be the delayed version of the original signal, right? So that is the difference between autocorrelation and cross correlation, okay? The difference between the correlation and convolution operation we have seen. If you observe their formula, so the summation variable are simply different here, but you can use here instead of n, you can even use k variable here. So k is equals to minus infinity to infinity x of k into y of k minus l will be there, right? So you will find the same type of operations, simply folding operation is not present in the correlation operation, right? But folding is present in case of convolution operation, while the remaining operations are similar in case of correlation and convolution, that is shifting, multiplication and addition, okay? And we've also seen the difference between here the cross correlation and the autocorrelation. The main purpose of the correlation operation is to compare the given signals, okay? You are identifying the degree of similarity between the two signals, okay? And it has various application in various application domains, okay? So in next session we will be discussing one example, okay? We'll be solving one example, we'll be provided with two signals and we'll try to identify the correlation of those two signals, okay? So thank you for joining today's session.